Molarity is one of our most commonly used conversion factors and units of concentration, especially in general chemistry. Okay, you're going to be using this for Chem 1 and Chem 2. It's going to become second nature to calculate molarity. But molarity is a capital M, so a few different M's you're going to see. If I just write a lowercase m like this, I mean mass. If I write a script m like this, I mean molar mass, which again is grams per mole. If I write a lowercase m like that with a little front tail on the front end, it means molality, which we'll talk about in the beginning of Chem 2. And if I write a capital M, I mean molarity. We only have 26 letters and we only want to use like 15, so you're gonna have to get used to it. But molarity, capital M, is used to describe solution concentration because it's a very easy way to determine the number of moles of solute that you have present in your solution. So again, moles of solute over liters of solution. You can absolutely use this as a conversion factor, and we will use this as a conversion factor. Students tend to forget, though, that it's such a nice conversion factor. So I'm just trying to emphasize that very clearly so you guys don't, in fact, forget. It is a great conversion factor for you. So when I say 0.5 molar NaCl, I can rewrite this as 0.5 moles of NaCl per 1 liter of solution. Doesn't matter if I don't have 1 liter of solution. By the molarity, if I had 1 liter, it would be that many moles. If I have less than a liter, I can figure out how many moles I actually have. But 0.5 molar means 0.5 moles over 1 liter of solution. Or I can flip that upside down, which students do not like to do as much, but you need to recognize it is a conversion factor. It can flip. 1 liter of solution would contain 0.5 moles of NaCl. Be careful here, though. You have to think about how these things are splitting up. Down here, we have an example of a 0.50 molar solution of magnesium chloride. What this means is think about the way magnesium chloride splits up. MgCl2 splits up into Mg2 plus and 2 moles of Cl minus. Now we've already learned this in a previous chapter, but if I do the stoichiometry here, the conversion factor, this means 0.5 molar here gives me 0.5 molar here because it's a 1-to-1 ratio, but it gives me 2 times 0.5 molar here, which is the same as 1 molar for my chloride ions. And my sig figs should be 2 sig figs. 1 molar chloride ion. I have twice as many chloride ions as I do magnesium chloride. So therefore, if I have a 0.5 molar magnesium chloride, I have a 1 molar chloride ion solution. I have a 0.5 molar magnesium chloride solution, therefore I have a 0.5 molar magnesium ion solution. Because this compound is going to split apart in water. We're going to talk about how we're going to know that. We're going to talk about our solubility rules. But you need to be able to recognize how it's splitting apart and recognize the stoichiometry behind it. Okay, so again, molarity, moles of solute over liters of solution. We can also, if we have molarity, multiply by our volume in liters and get back to our moles of solute. We're going to do that a lot. The capital M can be rewritten as moles per liter, and I highly recommend you do this anytime you get to any sort of math. If you're doing it for a final answer and calculating molarity, write that capital M, absolutely. I will give you that capital M in equations and examples, 100%. But if I'm using molarity in a conversion at all, I'm going to write moles per liter so I don't miss my conversion. So it is a conversion factor. It's going to convert between moles of solute, liters of solution, and concentration of solution. That's right. Let me write it on this page. So in order to say it, we do say, like, let's say I have something that's written as 0.25 capital M HNO3. The way I say this is I would say 0.25 molar HNO3 or 0.25 moles per liter HNO3, okay? So we do say molar for that capital M. And when you say molar, we know you mean molarity. Let's do an example. How many grams are needed to prepare a 1 molar sodium chloride solution in a 1 liter volumetric flask? Well, the picture here is describing it to us, but let's go ahead and do the math anyway. I need to know how many grams. So what I'm trying to find here is how many grams, okay? I know that I need a 1 molar sodium chloride solution, and I know that I have a 1 liter volumetric flask. So write down what I want to know first. I want to know number of grams of NaCl. Next up, write down one of the two things you're given. I don't have any preference really what number you start with. Some students really want to start with the 1 liter. I tend to start with the concentration. I don't know why, I just do. So I'm going to write that down first. I'm going to write down 1 mole NaCl per 1 liter of NaCl solution times, now this is how much I know I need a 1 molar solution, but I'm told I have a 1 liter volumetric flask, which means that volumetric flasks are very specific volume, which means that if I prepare it in there, I'm going to have 1 liter of the sodium chloride solution. So notice what I've done so far. I'm going to move this up here so that we can finish writing it out. What I've done so far is just converted. I've canceled out my liters. So now I know how many grams I need is based on 1 mole. To make this solution, I need 1 mole of sodium chloride. That may seem intuitive because we're asking for a 1 molar solution, but that's only working because we have 1 liter. We won't always have an entire liter of solution we need. We may need less a different time. So we have to pay attention to that step, okay? And it also shows us our cancellation of our units. Now, I want to get to moles, or I want to get out of moles, so I need to cancel out moles and get to grams. I know my molar mass is my conversion from grams to moles. If I look up sodium chloride, or if I add it up, sodium has a molar mass of 22.99 grams per mole. Chloride, 35.45. So the molar mass is 58.44 grams for every 1 mole. That cancels out my moles of sodium chloride and gives me grams. So I calculate it out and I get 58.44 grams of NaCl. Now, sig figs wise, let's see, I've got 3 sig figs. I need to round this to 358.4 grams of NaCl. In the real world, when you're working with a balance, you're probably not going to have it to 1 decimal place. It's probably going to be more. You just want to get as close to that as possible. So let's see what they did here. Preparing a solution is specified concentration. We have to add 1 mole of sodium chloride. Well, we've determined that 1 mole would weigh 58.44 grams. And good thing we did our math right. It's confirmed here. They weighed out 58.44 grams of NaCl, and they added it to that volumetric flask. They then added water. And what you're going to do is you're going to add water. In the real world, you're going to add water to about right here, and you're going to shake this like crazy until all of it dissolves. And once dissolved, there's a mark on the graduated cylinder, which is called your 1 liter mark. So this has a mark at 1 liter because it's a 1 liter volumetric flask. You add water until you get to that point, when your meniscus reaches that point, and then you know that you have the perfect volume. It's exactly 1 liter. Mix up that solution really well, and if you use 58.4 grams of it, you will have a 1 molar solution. Let's do another one. How many moles of HCl are present in 320 mils of a 0.25 molar HCl solution? Okay, so what I want to know is how many moles. I'm starting with 320 mils, and I've got a 0.25 molar solution. So number of moles, HCl. Again, you can start with either number here. I just, for whatever reason, really like to start with molarity. So 0.250 moles of HCl in every 1 liter of HCl solution. Notice I am emphasizing what the solution is of here, and that's because pretty soon we're going to be converting between different species, like we've done with stoichiometry, and it gets really confusing if you're not labeling what you have. So please label what you have with the species you're talking about. I'm going to multiply that by the volume in liters, so convert this to liters. You don't have to show me the conversion, but you should be able to do the conversion, okay? 320 mils becomes 0.320 liters of the HCl solution. This cancels the solution, gives you moles, and I see I have 0.0800 moles of HCl. What about this one? What is the concentration of the solution described? Well, let's see what's happening here. We got some ammonium dichromate, NH42Cr2O7, and I see here on the picture that I'm adding 90 grams. So to my 250 ml flask, I've added 90 grams of ammonium dichromate. I then have a graduated cylinder here of 250 mils, and what you can't see here is cut off by the picture. This originally said A, this originally said B, this originally said C, okay? So in A, I weighed out 90 grams of ammonium dichromate. In B, I added the 90 grams of ammonium dichromate to a 250 ml volumetric flask, and I have a graduated cylinder here with 250 mils of water. In C, I see that I've got that flask filled to the mark, which means it is filled to 250 mils of total solution. And I have 45 mils of water left over. Okay, so let's talk about what's happening here in the pictures. We added the solid to the volumetric flask. We then added water. We dissolved that solid in the water. So this is my solute. This is my solvent. And once the volumetric flask has been filled to 250 mils of total solution, so solute plus solvent equals 250 mils, I have some water left over. This picture very intentionally shows you that, and it's because this has a volume that adds to the total volume of the solution over here. That's why you have the 45 mils left over, because 90 grams of ammonium dichromate takes up space. It takes up about 45 mils of space. Okay, so you're never adding 250 mils of solvent to the system. We're adding solvent plus solute total to equal that 250 mils. But I want to know concentration. So remember, your concentration is number of moles of my solute. So my NH4,2Cr2O7 over my liters of my NH4,2. Okay, we're going to call this solute because it's going to be much shorter to write solute over and over. Number of liters of solute. Solution. That's what I'm trying to find. I don't know my moles. I don't know my liters yet, so let's figure it out. Well, I'm starting off with 90 grams of my solute. And I've put it into 250 mils of total solution. I can do that conversion in my head. 0.250 liters of solution. I've got my denominator set. My liters of solute solution, my liters of solution. So that's set. The reason I'm saying solute solution versus solution, solute is emphasizing that it's in that solution. It's emphasizing that you've got your solute plus your solvent in that solution, okay? So I've got my denominator set. I need to work on that numerator. Got 90 grams of that solute. I need moles of solute. 1 mole of solute, well, add up ammonium dichromate. Ammonium, nitrogen is 14.01, hydrogen is 1.008, chromium is 52.00, oxygen is 16.00. When I add up the molar mass here, I'm going to get 252.1 grams per mole. So 1 mole will equal 252.1 grams. Calculate that out, and you end up with concentration of 1.43 molar. And now that I have a little bit of space, I'll write it. NH4,2Cr2O7. So again, some people want to do this in parts, and that's fine. You could have found the number of moles first, found the number of liters of solution separate, and then divided them. But I figure, why not just do it faster? I know I put this many grams into this volume. That's what I need for my ratio anyway. Let's find our solution concentration. So 1.43 molar ammonium dichromate solution is prepared if you mix 90 grams of ammonium dichromate into 250 ml of total solution. What about this one? A solution contains 6.00% by mass sodium bromide. The density of the solution is 1.046 grams per centimeter cubed. What is the molarity of the solution? Okay, students really don't like this question because they get really confused on what to do here. This is pulling back from a couple chapters ago when you're given percent by mass. Percent by mass means you assume you have 100 grams of whatever is coming after it. So in this case, assume 100 grams of solution. By doing that, this would mean that I have 6.00 grams of my sodium bromide. I have 100 grams total solution, and I'm going to put my sig figs right there because I have 6.00 and that has 3 sig figs. I'm going to assume the 100 has 3 sig figs as well. I'm going to match that 100 to the sig figs within my percent, okay? So if I assume I have exactly 100 grams of solution, which is solute plus solvent, then I know I would have 6 grams of solute in there. So I know what I want is molarity, right? I know I want number of moles of NaBr over liters of solution. But I don't have either of those pieces yet. So I'm going to do them in parts and then put it back together up here. So first, let's talk about the number of moles of sodium bromide. If I have 6 grams, sodium bromide, I apologize. If I have 6 grams of sodium bromide, I'm going to convert to moles. 1 mole of sodium. 1 mole of sodium bromide. Sodium is 22.99 grams per mole. Bromine is 79.90 grams per mole. So sodium bromide has a molar mass of 102.9 grams per mole. This gives me a number of moles of 0.0583. So I know my numerator, 0.0583 moles of NaBr. Now, I'm going to use my density to find my liters of my solution. So number of liters of solution. Remember, we assumed 100 grams. But I have the density right there. Density is telling me that 1 centimeter cubed is 1.046 grams. I don't want centimeters cubed, I need liters. Well, I know that 1 milliliter is 1 centimeter cubed. And yes, I need to include that conversion for my credit. Mathematically, it doesn't appear to do much, but it converts your units correctly. So 1 mil to 1 centimeter cubed, that would get me in mils, but I want liters. 1 liter is 1,000 mils. So I get 0.0956 liters of total solution. That's my denominator, 0.0956 liters of solution. When I calculate that out, I'm going to get an answer here of 0.610, so I've still got those 3 sig figs, 0.610 molar NaBr. So a 6% by mass sodium bromide solution is the equivalent to 0.610 molar sodium bromide. Okay, let's talk a little bit about particulate diagrams. This is kind of going back to that idea of being able to picture what's happening in solution in your mind, okay? Given the diagram for 0.20 molar KCl solution below, sketch the rest of the solutions. The white space is water in this sketch. So this is telling me I have 0.20 molar KCl. Cool. What do I do with that information? I'm going to look at the system and see. What this is trying to do is it's trying to say I've zoomed in on this little area right here, and this little area right here is this circle of particles here, okay? So I see that I have 4 K pluses and 4 Cl minuses in solution. It shouldn't surprise me that it's a 1-to-1 ratio because KCl, for every 1 potassium ion, there's 1 chloride ion. So I expect that 1-to-1 ratio. But I see a 0.2 molar solution is being represented by 4 of each particle. So if I wanted to zoom in and look at a 0.1 molar, I expect this to be half as concentrated. 0.2 molar has 4 of each particle, so 0.1 molar must have 1 of each particle. And you can write them like this, you can mix them up, it doesn't really matter. You know, some people want to write them like this. It doesn't matter, the ions are floating around in solution. But if I have 0.2 here, that means I have half as many particles over here. What about a 0.1 molar magnesium chloride solution? Well, I know that my 0.1 molar solution had 2 particles of potassium and 2 particles of chloride. But notice that this is 0.1 molar magnesium chloride. And we talked about magnesium chloride a little bit ago. But when magnesium chloride splits up into solution, it splits up into 1 magnesium ion and 2 chloride ions. So for every 1 magnesium, I have 2 chloride. If I have a 0.1 molar magnesium chloride, that means I have a 0.1 molar magnesium ion, but I have 0.2 molar chloride ions. So I'm going to have 1 magnesium, based on my previous diagrams, I will have 2 magnesium ions present, and I will have 4 chloride ions present. Because there's twice as much chloride as there is magnesium, but the 0.1 here is telling me I'm matching to my system over here, which is 2 particles of each, so 2 magnesiums. And then double the amount of chloride. The other one I have down here is HF, and we haven't spent much time talking about HF yet, but HF is a weak acid. Meaning it does not fully break up in solution. So what's going to happen here is you're actually going to have, I apologize for my drawing skills right at this moment. These are both pretty small, but H and F, H and F. A 0.1 molar solution will have 2 particles, but they most likely aren't going to break apart at that point. HF is only a couple molecules are going to break apart, so most likely they will look like this. At absolute best, you're going to have 1 molecule together, and then 1 H plus and 1 F minus, but HF does not break apart that much, so really it's going to look like 2 little particles floating around. And we will spend more time talking about weak acids later in this chapter, and also a lot of time in Chem too, so you'll get more comfortable with that idea.